Okay, so today we're going to talk about Lagrange interpolation. Okay, so we're going to consider constructing a polynomial of degree at most n that passes through the n plus 1 points. And those points are given by x naught, f of x naught, x1, f of x1, all the way up until xn, f of xn. Okay. And for each k equals 0 through n, we will construct a function L with the property that L equals 0 when I is not equal to k, and when L equals to 1 otherwise. So in order to satisfy this condition that L equals 0 for I is not equal to k, we need to require that the function L contains a certain quantity in the numerator, and that quantity is x minus x naught times x minus x1 times x minus x k minus 1 x minus xk plus 1 all the way through x minus xn. And to satisfy the function L equals 1, the denominator must be the same thing but evaluated at x equals xk. And so that's going to look like xk minus x naught xk minus x1, xk minus xk minus 1, xk minus xk plus 1, all the way through xk minus xn. So now we're going to define the nth Lagrange interpolating polynomial. And so if x0, x1, all the way through xn are n plus 1 distinct numbers, and f is a function whose values are given at these numbers, a polynomial p of x of degree n exists. So that would look like f of xk equals p of xk. For all k equals 0, 1 through n. And that's given by the sum from k equals 0 to n f of xk times L of x for all k and we can define that function L of x and of course the denominator has to be evaluated at x equals xk. This can also be represented as a product. So a product from I equals 0 to n, where I is not equal to k, would be the quotient x minus xi over xk minus xi. Okay?
Hi, so in order to implement the Lagrange interpolation, we can use a VBA spreadsheet. Um, Typically, this is going to act on these set of points, x and y, or x and f of x. So we can enter some data into a spreadsheet to perform that subroutine for the Lagrangian interpolation. So let's say we have some data. X, and we have some data for f of x. Okay, and we want to approximate a polynomial for this data. When we use a Lagrangian interpolant, there's an order at which that interpolation occurs. The product involving the I equals 0 to n, where I is not equal to k, that n is the order, and we can describe that order in a spreadsheet. And so the nth order Lagrange interpolating polynomial in this case would be 2. So the second order interpolating polynomial. And we can interpolate at some value. Let's say we're going to interpolate at x equals 10. Okay. And then what's the value of f of x using our Lagrangian interpolation? So we're going to go to Developer, Visual Basic, Insert Module, and start with our subroutine. So that's going to begin with let's call the subroutine Lagrange Interpolation. We are going to dim our variables, arrays. So for our product, we're going to need that order n and an indice I. And since x is an array and y is an array, we need to dim them as such. So we'll say that array x can hold 10 values. We can set that to whatever we want. We can make that 100 or 1,000, but 10 should be enough to contain this data here. We're going to do the same thing for y. This data here. And our the point at which we're interpolating, which I think we said was 10, we'll call that xi. And we'll make those double precision. Okay. So we need to write something to select our x data. So we're going to do a for loop to scoop up this data here. So for I equals 0 to 10, given that this holds 10 values, we're going to say x of I is equal to the range A ampersand I plus 5. Okay. So A stands for this column here, column A, and I plus 5 indicates that our data starts at the 5th row. Okay. So if we wanted to start at the 6th row, we could say I plus 6. If we wanted to start at the 7th row, we could say I plus 7, etc., etc. But our data starts at the 5th, so we're saying I plus 5. We're going to do the same thing for Y. Select our Y data. Or, yeah, that's fine. Or f of x. We're going to do the same for loop, except this time it's Y. And our range is in the B column. Okay. We also need to select the point at which we are interpolating about. So we're going to select our xi. Xi equals the range E4. So column E, row 4, is 10. So this subroutine is going to read in whatever value we have there for our xi. We're also going to select the order of our Lagrange polynomial. And the order comes from column E, row 3. I'm going to choose a second order Lagrange polynomial. Okay. And then to close out our subroutine, we're going to message box and we'll come back to this later. Reason being because it's not going to make sense what we're outputting until we've defined a function that outputs what we need. Okay. So we're going to design some function. I can't spell today. Function. And the Lagrangian function is going to depend on the x data, the y data, the order of the polynomial, and the point at which we are interpolating about. So that's going to be x, y, xi, and order. Okay. We need for the product, we need two indices, I and j, or I and k. It doesn't matter. We'll just say I and j for simplicity. Those are going to be integers for the product, and we need to double precision the terms in the product. Okay. So we initialize the sum. We can say the sum equals 0. And then we need to do a for loop. So that upper bound on the product is the order of the Lagrange polynomial. I think we chose 2, so the order is 2. So for I equals 0 to 2 in this particular case. And the product is going to equal to the y data. And then for j equals 0 to order, we have if I is not equal to j, then the product equals the product times that quotient xi minus x of j divided by x of I minus x of j. And if for the next j, the sum is equal to the sum plus the product, next I, and then we're going to say that the Lagrange equals the sum. Alright, so now that we have a Lagrange function, we can message the output as a message box. The estimate of f of x is ampersand, and then we'll go ahead and put our call to this function. Okay, so let's go ahead and run it. The estimate of f of x is 4,672.81, etc. And it looks like we have estimated the polynomial given this data, the second order Lagrange interpolant around x equals 10.